This is a lesson about battery EMF and internal resistance. Well, most of the time in a circuit problem, you're dealing with what we call an ideal battery. An ideal battery is voltage. It's when the voltage across the terminals of the battery are independent of the current supplied. What I mean by that is if we have a battery, here's the positive terminals and the negative terminal. And if we were to hook a voltmeter up to this battery, okay, let's say that this is a 5-volt battery. So if we hook a voltmeter up to this battery across the positive and negative terminals, then our voltmeter would in fact read 5 volts. Okay. Now, what if we connected something to the battery? Perhaps a light bulb. So it's still a 5-volt battery. But this time we're going to connect it to a light bulb. Okay, so that now there's current flowing from the battery through the circuit. And now I'm going to hook up a voltmeter and measure the voltage difference between the positive and negative terminals of this battery. And if it's an ideal battery, I'm still going to get 5 volts. Okay. But real batteries are not like that. Real batteries have something that we call internal resistance. And because of that internal resistance, the voltage across the terminals depends on whether or not this battery is supplying current, and will in fact depend on how much current is being supplied. So let's look at an example of a real battery. Okay, real batteries can be thought of as a voltage source of potential difference with a positive terminal and a negative terminal. But in addition to that, there's an internal resistance, which we will call R, lowercase r usually. Okay, and for that reason, the voltage from the positive terminal to the negative terminal is not necessarily the same thing as the nominal voltage of the battery. Now, the nominal voltage of the battery we'll call the EMF, and we can note that with a script E. Okay, so E is the EMF. It used to stand for electromotive force, but because it's not actually a force, we don't generally use that term anymore. Usually we just call it EMF. That's an unfortunate name that was given to the internal voltage of the battery before we really understood what potential difference was. So just think of it as EMF. Okay, and by definition, the EMF is the potential difference across battery terminals positive and the negative terminal when no current is being supplied. Okay, so again, if the EMF of this battery is 5 volts, because it's a 5-volt battery, then if I don't have any light bulb connected to this battery, and I hook my voltmeter up to it, then it's going to still read 5 volts, the EMF of the battery. But what happens if I consider that the battery has some internal resistance and I cause it to supply some current? So I'm going to erase this EMF definition here so I've got some room. Pause if you still need to copy that down. Okay. So this time let's draw our real battery that has an internal resistance of R. Still have an EMF of 5 volts, and this time we're going to connect a light bulb to it. Okay, so there's our light bulb. We now have current flowing. Okay, but this time, if I hook a voltmeter up to it, I'm going to measure something less than 5 volts, because part of the voltage drop is occurring inside the battery at that resistor. Okay, so the EMF of this battery is still 5 volts, but the terminal voltage is going to be something less than 5 volts when I connect a resistor to it, something like a light bulb, so that current is flowing. And in the next video, I will work an example problem showing you how to calculate the terminal voltage of a battery when you have a certain internal resistance and a certain resistor connected to it.